circular measure, we need to talk about the radian measure, how we can use the radian measure to find the area of a sector of a circle and the arc length, so we'll talk about that. How you convert from radians to degrees, and then the relationship of that to angular and linear velocity. So that's the plan. So the radian as a measure of angle, conversion from degrees to radians and back again. Finding arc length and area of a sector, and finally linear and angular velocity. So that's the plan. So if we draw a circle and then we've got radius r, this is a circle with radius r, and I measure an angle so that this distance here, from there to there, which is called the arc length, and we use the symbol S to represent arc length, so that's the arc length. If we draw around the angle until this arc length is actually r, the radius, so that's the same, and if you think about it, it doesn't matter how big or small the circle is, the bigger the radius, the bigger this arc length will be, so the ratio stays the same, and this angle is always the same, and that's actually 1 radian. So if we've got that theta, which is the angle, is actually 1 radian. That's the definition of a radian. If you think about a whole circle and the circumference of a circle, that's 2 pi times the radius. So in other words, it's 2 pi lots of r, the radius. So a whole circle, in terms of radian, is 2 pi. So from this definition, definition of a radian, we have that a complete turn is 2 pi radians. And often we use rad for short, rad radians. So 2 pi radians is a complete turn. Because the radian is associated with a fraction around the circle, a part of the circle, rather than some arbitrary 360th of a circle is a degree, it's actually in terms of a distance around the circle. Whenever we talk about circular measure and angular and linear velocity and things like that, we tend to stick to radians, not degrees. So as time goes by, you're going to be using, certainly in mechanical engineering, the radian more and more, the degree less. We still use degrees in AC theory, for example. We talk about phase degrees. But even then, when we're putting angles into the formula associated with AC theory, we use radians. So it's going to be an angle that occurs an awful lot. So we need to be able to convert from radians to degrees and back again. So that's straightforward, because we know that a complete turn is 360 degrees, and that's equivalent to 2 pi. So there's our conversion factor. 360 degrees is 2 pi. And you remember that? Well, I do. I remember there's 2 pi radians in a complete 360 degrees. So you've got the conversion factor. What you can then do is say 180 degrees is pi. So that's maybe a more convenient way to think of it if you're actually doing the calculation. Now, if I want to convert from degrees to radians, what I could really do with is knowing what 1 degree is. So to go from degrees to radians, and I'll use rads for short, degrees to rads, what I could really do with knowing is what 1 degree is. And if 180 degrees is pi radians, what's 1 degree? Over 180. So there's my conversion factor. All I do is multiply my angle by pi over 180. E.g., um, 47 degrees is, so on your calculator you multiply 47 by pi over 180. Sorry? 0.82? 0.82 rads. So I've converted 47 degrees into radians. "90 degrees. Pi over 2, or we could convert that to a number. 3.142 over 2 is about 1 point something, but leave it as pi over 2. Now if you think about this, we go back to the circle. If 2 pi radians is the whole turn, then half a turn is going to be pi, and a quarter of a turn is going to be half pi. So that fits in with our picture of how it fits in with a turning round in a circle. Okay, what would 45 degrees be? Pi over 4, right, a quarter, and so on. So there are a few of these angles, like 45 degrees, 90 degrees, and so a few others that we can write down in terms of pi, and it's convenient to think of them in terms of pi. Now, if degrees to radians, I need to know what 1 degree is, so that's pi divided by 180. The other way, radians to degrees, then I need to know what 1 radian is. And if pi radians is 180 degrees, what's 1 radian? 180 over pi. The other way around. E.g., 2.6 radians is, so I multiply 2.6 by 180 over pi. Answer? 149 degrees. 3 pi radians. So often it's left in terms of pi, as we had before. How do I convert 3 pi radians to degrees? It's going to equal 3 pi times 180 over pi. And straight away, you see that pi's cancel, so that's 180, that's 270 outside. So 380, 540. Typical listener, 540 degrees, okay? So if you're given the angle in terms of pi, and that's why it's often in terms of pi, when we convert, the pi's cancel. So that gives us an exact answer, 540 degrees. Yeah. Okay, now 540 degrees, an angle of 540 degrees, in this scenario, we're talking about radians. We're often not talking about an angle in terms of what fraction of a circle have I gone through. So in other words, what's this? We're actually interested in how far it's turned. So actually we're thinking about, this is where the 540 degrees comes from. We're thinking we've turned through 360 degrees plus another 180 degrees, whoops, right the way around and back again, gives us a turn through 540 degrees. So if I could go and do 2 complete revolutions, that would be 2 lots of 360, 720 degrees, or 4 pi. So we talk about complete turns, and that's what we're going to be coming on to very shortly, this idea of rotation. So that's how we convert from degrees to radians and radians to degrees. We need to know this ratio. And that's not difficult to remember. All I've got to remember is that 2 pi is a complete turn. As soon as I've got that, I've got this, and then I've just got to remember, if I want 1 degree, it's pi over 180, 1 radian is